This equilibrium equation again we have expressed in the non-dimensional form, where q bar we have defined as q by q divergence, and gamma is defined as ratio of the nonlinear stiffness by linear stiffness. Then this equation, if I consider and give a perturbation to this equation, then we can get some idea about the stability of this system. In this, that's what I have discussed here. If we are taking giving a small disturbance to the system, we'll be getting this equation. See, from here I am giving a disturbance, which will be only for theta. Alpha r is the fixed value. So whatever perturbation we are giving, alpha r will not be getting affected. Only the effective angle of attack gets affected or changed, and that's why I have considered here the once we give the perturbation, the theta equilibrium plus delta theta, then plus gamma into theta equilibrium plus delta theta whole square minus q bar, again multiplied by theta equilibrium plus delta theta. This is the term whatever we are getting after giving a small perturbation to the system. The now what we have done, I have rearranged the equation. The first then the square term I am just expanding it. So theta equilibrium whole square plus 2 into theta equilibrium delta theta plus delta theta whole square, and this remains same. So after rearranging this equation, we can get one system, that is theta equilibrium plus gamma theta equilibrium whole square minus q bar into theta equilibrium. Then another part we will be getting as delta theta multiplied by 1 plus twice gamma theta equilibrium plus gamma into theta delta theta minus q bar greater than equal to 0. So we can get the solution of this equation like this. Suppose delta theta equilibrium equal to 0, we can get this term. The second term whatever we are getting from here, that is delta theta plus gamma delta theta whole square. Sorry, I think taking this delta theta equilibrium equal to 0, we can get from here itself, that is delta theta and gamma delta theta whole square plus q bar into delta theta, that should be greater than equal to 0. Now delta theta taking outside, whatever we are getting now, delta theta into 1 plus gamma delta theta minus q bar. So if we substitute the theta bar here, or in other way delta theta approximately equal to 0, so we are getting this equation 1 minus q bar greater than equal to 0. So in other way we will be getting a stability condition when q bar less than equal to 1. Under this quadratic equation or quadratic form of spring, whatever we have considered, or structural stiffness we have considered, for that if q bar is less than equal to 1, and then we will be getting the stability of the system. That means at q bar equal to 1, this system goes to divergence. Similarly, from the second equation, if we look at here, from the second part of this equation, whatever we are getting q bar minus 1 by gamma. So this is the solution of the equation, response solution of the equation, what we are getting. I have shown it one more derivation here. This is for another, it means delta theta multiplied by, if we look at delta theta multiplied by 1 plus twice gamma theta equilibrium plus gamma into delta theta minus q bar. That part if I am taking here and substituting the solution of the response, that is delta theta multiplied by 1 plus gamma q bar minus 1 by gamma minus q bar greater than equal to 0, and we are getting another condition. If q bar greater than equal to 1, then system will be stable. But the feasible solution, whatever we can think of from the practical point of view, this will be the feasible solution. The first one, q bar less than equal to 1 is equal to the system will be in stable equilibrium, whereas this, though it gives this solution, but before reaching this, it reaches, means it crosses this particular information whatever I plotted, q bar less than equal to 1. So obviously the system means from lowest divergence point of view, we can take q bar equal to less than equal to 1, or at q bar equal to 1, the system will be diverging. Now let me come to this nonlinear cubic equation. Here we are taking the elastic moment in terms of the linear spring and the cubic spring. And aerodynamic theory, we are still continuing to take as linear theory. So L prime into E into C, that is A prime, whatever we are getting, lift value, that is Q CL alpha into C multiplied by EC. So we are getting E square CL alpha into alpha. And this alpha we are substituting here as Q E square CL alpha multiplied by alpha plus theta. Now, coming to the equilibrium condition, when the two moments, that is aerodynamic moment, is balanced by the spring, elastic spring, then we are getting ma equal to me, that is aerodynamic moment equal to elastic restoring moment. And the aerodynamic moment, what we are getting, whatever expression we have derived, that is q e square alpha multiplied by alpha plus theta, and then aerodynamic structural stiffness k theta naught into theta, then k theta 1 into theta q. Here I have continued to take k theta 1 because we are taking there is no other k theta term, that's why I have continued. But if we are taking all the nonlinearity, let's say linear, quadratic, cubic, then accordingly we can give the subscript of this coefficient. Now dividing whole equation by k theta naught, this equilibrium equation whatever we have obtained, now I am dividing by k theta naught and defining one more parameter, that is q divergence is nothing but k theta naught by E c square CL alpha, that is the q divergence. We can write now, after substituting that value, we can write now the equation will become q by q divergence into alpha r, this is alpha r into theta, alpha plus theta, and right hand side will be theta plus k theta 1 by k theta naught k theta q. Now whatever we have defined, q bar is equal to q by qd, and k theta 1 we are taking as gamma. So in this gamma, whatever we are getting, gamma equal to k theta 1 by k theta naught. So this equation finally we are getting as gamma theta q plus gamma theta minus q bar alpha r plus theta. Let us consider alpha r equal to 0. just for sake of the getting solution, analytical solution. Otherwise, there is no meaning of taking alpha r equal to 0. If I am taking alpha r equal to non-zero, then we may not get the analytical solution. That's why in this derivation I have considered as alpha r equal to 0. But when you are developing a code where you can calculate the numerical value of theta, there we may not need to consider alpha r equal to 0. And if after substituting this alpha r equal to 0, this equation we are simplifying into this form. So theta multiplied by, if you look at here, this term will be 0. So it will be theta multiplied by gamma theta square plus 1 minus q bar, that whole thing equal to 0. Here the two solutions we can get. One is theta equal to 0 and theta 2 and theta 3. The first root is 0. For this we can get, obviously theta is 0, the system will be in equilibrium. Means whatever alpha r we are giving, it will be continue to be in that, basically in that, that is in this case whatever theta 1 equal to 0 we are getting, that is a hypothetical solution. But practically it does not have that this value. We can have theta 1, theta 2 and theta 3, whatever I have shown it here, the expression that is equal to plus minus square root q bar minus 1 divided by gamma. This is the other two solutions. So let us now go to the calculation of, this is the response solution, means with the cubic nonlinearity, one solution I am getting theta 1 equal to 0, and the other two roots theta 2 and theta 3, that is equal to plus minus square root q bar minus 1 by gamma. So, if you look at here, suppose q bar is greater than 1, if it is q bar is less than 1, then whatever we will be getting the solution, that will be imaginary solution. So if you look at here, suppose q bar I am taking less than 1, so the numerator term will be negative. In this case, it will be negative. That means that theta 2 and theta 3, whatever we will be getting, the imaginary root. Imaginary root. What is the meaning of the imaginary root? Actually, the physical meaning of this, beyond q bar equal to 1, those values will be basically converged to this theta 1 equal to 0. If nonlinear cubic terms are there, if when theta q bar is greater than 1, then we will get some solution from here, which will be real solution. Is it clear, whatever I am saying here?
Yes, sir.
Okay. Let me just continue. So this is our response solution. Now suppose we are giving a small perturbation to the system. So if we am giving small perturbation to the system, we can get delta ME is k theta naught into delta theta, and k theta 1 into 3 theta square into delta theta. So that is coming as k theta naught multiplied by 1 plus thrice gamma theta square into delta theta. That is the perturbation whatever we are giving. With that delta theta perturbation, whatever restoring elastic moment will be developed in the system. Similarly, aerodynamic moment will be q e c square cl alpha into delta theta. So now we can consider three cases, that delta m is equal to delta ma minus delta me, that is substituting this equation q e c square cl alpha into delta theta minus k theta naught into 1 minus 3 gamma theta square into delta theta. So in other way, we can get it here at delta theta by k theta naught, uh, just dividing whole equation by k theta naught. So delta theta by k theta naught will become, this will become q bar when we divide whole equation. So it will be q e c square cl alpha divided by k theta naught. So this term is nothing but qd, q divergence, and the non-dimensional term whatever we will be getting, q by qd is equal to q bar. That's what I have taken it here, q bar minus 1 plus 3 gamma theta square, that multiplied by delta theta equal to if it is greater than 0, uh, sorry, in this case, as I have taken aerodynamic moment is here, so if it is less than equal to 0, then only system will be stable. So delta theta less than equal to 0, or in another way, q bar equal to q bar, if q bar is less than equal to 1 plus delta 3 gamma into theta square. What is the meaning of this? Means depending on the amplitude and the nonlinearity term, the q bar will be varying, which will be higher than 1. In this case, whatever we are getting, this 1 plus 3 gamma theta square. So this shows that our q bar will be coming as greater than equal to 1 plus 3 gamma theta square. Means as it is a nonlinear term, nonlinear cubic nonlinearity we are considering. That's why we are getting a value which will be higher than the linear divergence speed in this dynamic system. Let me come to know the energy formulation. Let's say we are interested to calculate the total potential energy. Whatever nonlinearity I have considered, k theta naught into theta plus k theta 1 into theta cube, the whole thing multiplied by delta theta, integrating from 0 to theta. So after substituting the integration, so we'll be getting k theta naught into theta square by 2 plus k theta 1 into theta to the power 4 by 4. And
Sir,
similarly, W, yes,
sir,
uh,
uh,
yeah,
uh, so this stability condition which you have mentioned, the delta m should be smaller than zero. So, like if I'm disturbing it in the positive direction, then it should be smaller than zero. But if I'm disturbing it in the negative direction, it should
obviously,
be greater than zero.
yeah, obviously, in this case, delta theta, whatever we are considering, it will be in positive sense. You see, all our derivation based on the positive theta. If it is negative theta, then it goes to different, means instead of giving positive delta theta, if we are giving negative delta theta, then it will be different. And also another thing, whatever effective moment I have considered, if you look at, I have taken aerodynamics first and then elastic. Then whatever we are getting, delta m should be less
Yes,
than equal
yes,
to less than. If I am taking delta m to this delta m minus delta ma, then I'll take delta ma greater than should be greater than equal to 0. Okay. So these are how I am means the user how they are defining the system. With respect to that, we have to finally we have to keep in mind that elastic restoring force should be greater than aerodynamic moment, whatever developed in the system.
yes,
Okay. And
yes.
whatever you are saying, delta theta, we are considering here in the positive sense. If it is negative, then it will be reverse. But in general, when I'm taking as a positive theta, this will be actually, if I take negative, then it will be greater than equal to. And if you rearrange, you will be getting means less than equal to that. Let's say if I'm taking delta m equal to uh, sorry, greater than equal to 0 with delta theta as negative less than 0, then q bar will be, obviously then I have to take that sign term also here. Then it will become, this will become plus 1 plus 3 gamma theta square equal to greater than equal to 0. Correct. Is it okay now?
Yes, sir.
That's what means. Usually, whatever derivation we do with the positive sense, delta theta as a positive sense, but when we are taking negative, then appropriate equation has to be modified. The equation has to be modified. Instead of minus whatever I have taken with the delta theta equal to less than 0, greater than equal to 0, then I will be getting this equation. If I am getting delta, this delta theta less than 0, that is in the negative direction, then I have to take this as a positive. So actually it will be coming, finally q bar will be less than equal to 1 plus sorry, 3 gamma will be there, 3 gamma theta square. It will be that equation. Okay. Is it fine, no?
Yes, sir.
Okay. Uh, so let me continue whatever energy equation I was discussing. So if we calculate, this is the potential energy, whatever energy stored in the elastic system or related to elastic restoring force. So this k theta naught into theta square by 2 plus k theta 1 into theta 3 over 4 by 4. And similarly the work done, this is W is work done. So Q integrating from 0 to theta, Q E is square cell alpha, alpha plus theta equal multiplied by delta theta. So after integrating and substituting the integration limit, we'll be getting as Q E C square cell alpha multiplied by alpha plus alpha r into theta square by 2. And now, if we calculate this total
Sir,
potential energy, yes,
sir, I can still see your previous slide only.
it is not changing.
Yes, it has changed now. Okay.
Okay. Are you able to see this slide? It is with the energy formulation.
Yes, it has changed now, but your internet is lagging, I think, because
Maybe a little slow here. Okay. So anyway, just whatever I am saying now, we are calculating total potential energy, W minus U. In this case, I have taken W minus U. That means work done by the spring aerodynamic force minus the potential energy. That is the potential energy, whatever stored in the system we have considered. And substituting the equation, we will be getting uh, q into e c square cell alpha multiplied by alpha r into theta plus theta square by 2 and minus k theta naught into theta square by 2 and similarly minus k theta 1 delta theta to the power 4 by 4. This is the expression finally we are getting with respect to the total potential energy. Now we can get the first condition, that is delta theta by theta equal to 0. That will give us the equilibrium condition, that is q e square cell alpha alpha plus theta minus k theta naught into theta minus k theta 1 into theta cube equal to 0. That is essentially whatever equation we have shown in the other case. That is this equation basically considering the equilibrium of the system, we are getting back that same equation q1 plus theta minus theta minus gamma into theta cube, and the stability of the system we can get taking the second derivative del 2 pi by del theta square. After rearranging this equation, so q is square CL alpha plus minus k theta naught minus 3 k theta 1 theta square equal to 0, or in other way this should be less than equal to 0. In this case, as we have taken the work done first and then potential energy, so this has to be less than equal to 0 for the equilibrium. Stability, and also for equilibrium also. Q bar, so we are getting this should be less than equal to 1 plus 3 gamma theta square.
Sir,
Now I
shouldn't
am just
the second derivative be smaller than 0 for stability and not 0?
equating equal to 0, that will be we will be getting the condition of stability. Means at this point it will be divergent. This is the transition point. Okay, and if it is less than equal to in this case, whatever we have considered should be
So for stability, it should be a minima, right?
yeah, it should be minima.
So, the conditions for minima is second derivative should be smaller than 0.
Okay, it is not always minima, it may be maxima also. See, if we typically consider this type of system, suppose we are taking a ball and we are giving a perturbation to this system, this is stable. But in this case, it will be like this. Either you give positive or negative, the disturbance, it will be going to, but at this point when it is there, that is in stable equilibrium. But both sides it will be unstable. Okay, it is similar kind of situation here.
Yes, but uh, the ball on the left side that resembles a stable equilibrium, so second derivative should be smaller than 0.
This one. No,
Yes.
this system is fully stable system. Means whatever I am getting here, this q bar is less than equal to this one. Okay. In this case, we have considered this way, but suppose we take this pi equal to u minus w. U is the potential energy stored in the system. Then actually we need to consider the del 2 pi. Means I am saying sometimes mathematical equation, whatever we are getting, uh, sorry, obviously, okay. This should be equal to less than equal to 0. Yeah. Then it will be stable. It should be always del to pi by del theta square less than equal to 0. Is it okay?
Yes, sir.
So let me come to now the concept here. Means graphically, suppose we take this is our aerodynamic force, movements, whatever developed. In our linear system, what we have considered that ma, aerodynamic moment, is equal to q e c square cl alpha into alpha r plus theta. So the ma is linearly varying a curve like this, and in other case the elastic restoring force will be starting from here, because we have initially given a alpha r. For that alpha r there is no elastic restoring force, because it is kind of rigid body displacement. That is, through our control mechanism we are introducing this alpha r, and then elastic restoring force will be started developing linearly. Again, me, whatever we have considered k theta into theta, that is linearly varying elastic restoring force. So it will be means some curve like this, and this will be the point where these two values, elastic restoring moment, will be equal to the elastic aerodynamic moment developed in. So this is the point of equilibrium. If it is this theta is greater than less than equal to 0, then we call this system is stable. And if it is theta greater than equal to 0, then it is unstable. Okay? So this is just a graphical representation of this linear system, whatever
Yes.
we have considered. Now I'm just showing you, suppose we are taking a aerodynamic moment or a linear aerodynamics and nonlinear spring model, then something like this, we will be getting something like this. So suppose we have considered alpha, in this case actually alpha equal to 0. Suppose we take the alpha value, sorry, this will be alpha. Alpha r is something like this. So we may have, it is a cubic nonlinearity or quadratic nonlinearity, we may have a instability or critical point above the linear system, whatever we have seen here in this. And depending on basically the nature of this car spring model, we can get the system like this. This is our means when theta is less than equal to 0, sorry, less than equal to this point, this value theta critical, then the system will be stable. If it is above this, then there is a possibility, means actually in this configuration, whatever we are getting, beyond this, elastic restoring force is more than aerodynamic force. So obviously it will be stable, always it will be stable. But at this point, it has the tendency. So we can get similarly, suppose both aerodynamics and means we are getting cubic nonlinearity of this type, linear aerodynamics and nonlinear spring, then we can have something curved like this. It can means intersect the aerodynamic line of aerodynamic movement at two different points, whatever we got the solution in the case. That considering quadratic nonlinearity or cubic nonlinearity. Let me now come to the graphical representation, whatever we got. We have obtained the value of theta like this. Theta is q bar alpha r divided by 1 minus q bar Then for various values of alpha r, actually this alpha r is increasing value, and in this case alpha r is decreasing value. So this is the response whatever we are getting from this curve. We have derived this equation is equal to q bar alpha r divided by 1 minus then means when alpha are equal to 0, what will happen up to the critical divergence speed? There will not be any deformation, but suddenly it will be diverging from here. That is typically whatever we get critical buckling load of a Euler column. And if alpha r is greater than 0, then we
Sir,
may
your
get some.
sir, your voice is
Hello,
breaking too much.
is it breaking too much? Just 1 minute. Let me just check. Is it okay now? Am I audible?
Yes, sir.
Just I have shown it here for a linear aeroelastic system, considering linear aerodynamics and linear spring model. Um, Whatever response we get, this theta is q bar multiplied by alpha divided by 1 minus q bar, and this means the system will be unstable when theta is greater than equal to this sorry, q is q bar is greater than equal to 1. In this case, q bar is greater than equal to 1. Means the denominator part is equal to 0, 1 minus q bar is equal to 0. We get a theta value is infinite. That's whatever we are getting a response like this. When alpha equal to the value 0, we are not getting any theta value. Suddenly at the critical point, the system will be diverging. And with the increased value of alpha r, we may get a deflection which is coming before it is reaching the critical point. So same thing we have I have shown it here how we can represent this curve. Means if we are expressing this theta by q equal to theta by qd plus alpha into by qd. So it is a typical linear equation where I have expressed theta by q as y-axis and theta as in the x-axis. Then whatever curve we will be getting, it will be typically a straight line curve, and from there I'll be able to get the critical divergence speed from the slope of the linear equation or the straight line equation. This m is nothing but the 1 by qd, that is the slope of this. Means typically it is like this. Suppose we are considering a wind tunnel test, and at this let's say I'm seeing it from the top view, and there is a flow in this direction. So with a initial angle of attack, the deflection whatever we are getting here, theta is alpha, the value is this. So at theta equal to 0, we will have this non-zero theta by q bar q, and increasing this value speed, what will happen? We will be getting the, at some other point it will be getting stabilized, which is basically this theta. Let's say we are increasing the speed, then we will be getting that. Again we are increasing, obviously whatever I am talking of, that this curve will be, means points will be perfectly linear. From the experiment will not get perfectly linear point. We'll be getting a scatter point, but we'll be drawing a straight line through that, mean straight line through that, and slope of that curve can be calculated or measured from the this graphical representation, and this QD will be nothing but one of the means slope of this, 1 by slope of this curve. This is typically whatever we get from the Southwell plot, whatever you have done the experiment with respect to a column, and we are giving a compressive load P, and for different value of P, we will be getting the deflection. There, with the buckling analysis, what we get? This is Q, delta P delta. Then straight like this. When we discussing about the wind tunnel models, and then we will be coming to this representation once again to explain the experimental way of measuring the this divergence speed. Now, let's say I am taking aerodynamic nonlinearity and structure is linear, where I am taking quadratic aerodynamic load. So, whatever we are getting, basically a route, one route is coming like this, going this way, another route is coming from this and going this way. This is with the positive value of alpha. Alpha r is greater than 0, and whatever route I am getting, this is related to alpha r less than equal to 0. See, one set of, when I am taking alpha equal to non-zero, we will be getting one route like this. Up to this, there will not be any deflection, and at critical point, after this, the deflection will be suddenly started increasing. And another route will be starting from the beginning, maybe non-zero value, and then it will be asymptotically meeting that earlier route. These are the two different routes, and if I am going beyond this, then I have one more route coming. This is actually coming from the negative value of alpha. One is going like this, when I am taking alpha is less than equal to 0, the critical point whatever we are getting, that is lower than this point. The value of that is lower than the q bar equal to 1, and what will happen? One route will be diverging like this, means one route coming from here, another route coming from here, and then they are meeting together and then again diverging. Asymptotically it is going to the positive theta, and another is going to 0.
Sir, here in this graph, uh, which graph is for the aerodynamic moment and which graph is for the spring
No, no, no.
force?
Here it actually combined. It is the aeroelastic response. See, when we have taken the nonlinear aerodynamic load, quadratic load, and structural load, then whatever equation I'll be getting, basically I'll be getting k theta into theta equal to q e c square cl alpha uh, into alpha or Cl alpha naught into alpha and Cl alpha 1 into alpha square. So whatever response I am getting, root of this solution, whatever response it will be giving, that I am plotting here in this graph. So alpha greater than equal to 0, we have positive alpha. The roots are like this. It is a quadratic equation. We will be getting two roots, and when alpha is less than 0, then I'll be getting another set of roots which will be showing the behavior like this. Means for positive value of alpha, it will be the instability will start from here. It will not in the linear case, whatever we got suddenly it is diverging. It will not do that. It will be slowly progressing. Means deflection will be increasing beyond this point. And for alpha less than 0, the instability point will be lower than I have shown in mathematically. Is it clear?
Yes, sir.
Okay. What I'll be giving one assignment so that you can calculate these values and get the idea about how these roots are moving with different value of q for different set of alpha. See, if you look at, I have taken separate set of alpha. See, it will be ideal. Suppose we get only one theta value here, alpha equal to theta. So we can get two roots and we can actually here we have lot of values. Alpha are different values are there. That's why it is little bit whatever I'm getting. Let's say I'm taking this root equal alpha equal to 3 degree. I have got one equation here, one root is here. It will come from this 0 point, and then it is going like this. Similarly, I'll be getting
So your voice is breaking too much. We cannot understand what you're saying.
okay. Ah, no, no, I just I think I have theta here. See, theta, what I'm saying, for a quadratic value of quadratic nonlinearity, is it voice is clear now, or you are still there is a disturbance?
Uh, Now it is okay, sir, but at times it is not clear, sir.
Okay, okay.
So like maybe you can repeat this part in the tomorrow's class. Uh,
No, today we have a 2 hours class, no? Anyway, I'll discuss it if you are. Can we disconnect it and then connect once again? I think then we can check it whether
Now
it is coming
now
properly.
your voice is okay.
Eh?
Now it's okay. Now your voice is okay. We can hear you.
Now it is okay.
Yes, sir.
Okay.
But we can take a break. Uh,
Yeah, yeah. We can take a break and then we can come back. Probably then I'll just come out from this MS window, MS Teams, and then connect once again. Okay. So you take 10 minutes break.
Okay.
Then after 10 minutes, we'll join it back again. Let me take the attendance. Am I audible now? Hello.
Yes, sir. Yes, sir, you're audible.
Okay. Let me take the attendance. Rajesh Mina,
Present, sir.
Priyam Dalmia, Siddhant Raj Jindal, Siddhant, Aman Sangban, Phuni Sai Ganesh, Dikshit Rathod,
Present, sir.
Kajal Chaudhary,
Present, sir.
Chandramouli,
Present, sir.
Yuvraj Kumar,
Present, sir.
Borun Trishul,
Present, sir.
Aditya Deepak,
Present, sir.
Ajay Tanala,
Present, sir.
Jitendra Pradhan, Jitendra, Kotapulli Vivek,
Present, sir.
Sir,
ah,
Funny Sai Ganesh present, sir. I just came back from washroom. Number 8.
yeah, okay. Kritik Santosh,
Present, sir.
Rahul Rajkumar, Rahul Raj, Siddhant Gupta,
Present, sir.
Rahul, uh, Rahul Raj is there? Orghonir Giri,
Present, sir.
Astosh Das,
Present, sir.
Kotipulli Lilaram,
Present, sir.
Rafsan Singh,
Present, sir.
Devars Dharmendra Bhai,
Present, sir.
Shivam Pandey,
Present, sir.
Divya Datta, Divya, Shreyas Samudra,
Yes, sir.
Sai Harshit,
Present, sir.
Naga Venkata Satta Suryavardhan,
Present, sir.
Nikhil Pankaj Mantri, Chandupatla Sai Teja, Devanik Das,
Present, sir.
Visham Kumar Thakur,
Present, sir.
Purita,
Yes, sir.
Nitin Sharma,
Present, sir.
Divyashree,
Present, sir.
Kashrinath Chaudhary,
Yes, sir.
Vignesha M,
Yes, sir.
Vignesha,
Yes, sir.
Thomas Paul,
Yes, sir.
Nadeem Rahman,
Present, sir.
Aish Gupta,
Yes, sir.
Prithvi Narne.
Present, sir.
Anyone left? Chandu Patla Saiteja, Nikhil Pankaj Mantri, Divya Datta, Siddhant Gupta, sorry, Rahul Rajkumar, Rahul Raj, Jitendra Pradhan, Aman Sangban, Siddhant Raj Jindal, Priyam Dalmia. Okay. I was discussing here only. Is it visible now?
Yes, sir.
Am I audible clearly?
Yes, sir.
Okay. Okay. What I am saying here in this nonlinear velocity system, depending on the value of alpha, we'll be getting two roots, and I have just plotted for various values of alpha the initial angle of attack, and then plotted the root how they are varying with respect to the increased value of in this case, whatever we have taken is the non-dimensional dynamic pressure, that is Q bar basically. Q bar non-dimensional dynamic pressure for different value of non-dimensional dynamic pressure, how the roots are varying. So one root means when we are taking alpha equal to 0, the roots are actually 0, all coming up to this 0, then it is increasing. Then alpha equal to 3 degree, actually it is 3 degree and 5 degree. I have just by mistake I have given here 3 and 3, both are 3. Actually one is 3, another is 5. So for different value of alpha, what we are getting, one root will be getting 0 here, another root we will be getting something like this. It is varying over the Q bar, for different value of Q bar, how it is varying. Similarly, if I go to the quadratic nonlinear system with structural nonlinearity quadratic and aerodynamic nonlinearity, that is aerodynamic linearity, linear system, then again I have just plotted it here, how it is varying from this point. Here we are getting the roots are when it is structural nonlinearity is there, this root is straight, it is going a straight route, means the function of the theta with respect to q is linear for one root, another root it is quadratic, whatever we are getting here in this also. And when alpha is less than 0, that is negative value of alpha, we are getting some root like this, then some root like this, like this. Obviously, these are for different value of alpha I have considered here. Then I am going to cubic nonlinearity, also will be getting similar kind of behavior. Means what we have seen in the linear system, at critical divergence speed, suddenly the deflection of the torsional deflection of the the aeroelastic system will be very high. In the nonlinearity, we are not getting that. Suddenly, it is not increasing. It is progressively increasing for different value of q. In this case, we are getting here. If you look at for different value of alpha, whatever route we are getting, one route is going like this, another route is going this way. Similarly, we will have the two routes for positive theta also, for positive angle of attack. Sorry, it is negative, whatever I have taken it here, negative, then it is positive. So you will be getting, this is basically, we have plotted the response theta is varying for the non-dimensional dynamic pressure when we have taken structural nonlinearity, cubic nonlinearity, aerodynamic, linear. That we have to derive the same way, and for different value of alpha, I can get the numerical solution. In this case, whatever solution I have obtained, these are all numerical solutions, because only analytical solution we can get when alpha equal to 0. For any other value of alpha, we have to get numerical value. In solving that equation and getting the root at that particular value of q, whatever we are changing the dynamic pressure. Q is the non-dimensional q bar, basically non-dimensional dynamic pressure. Similarly, we'll get for taking linear, nonlinear aeroelastic system with structural cubic nonlinearity, aerodynamic quadratic nonlinearity. Here, if you look at, it has been shifted. The whatever we got, the car, this has been shifted. If you look at here, we got from it is diverging from here, but look at here, this point has shifted to some other location. It is not in the zero line. It has gone to little bit downward direction. That means with a negative deflection, whatever we will be getting. Okay. Is it okay, this nonlinear term, nonlinear aeroelasticity part? Or if you have been doubt, just you can ask me now. So if it is okay, then we will proceed to the next topic. This slide is visible. Hello.
Yes, sir.
Topic I will be covering, that is internal testing related to elasticity, or even in aerodynamic theories. whatever we calculate based on certain assumptions, obviously that is not always acceptable. We have to prove that in the wind tunnel model, experimental model, where we can take a simplified model of the full aircraft, either wing part of the aircraft or the whole aircraft, and we can place in the wind tunnel to record the data of pressure and also response of the system. So if you look at here, we can have three different type of models in the wind tunnel. One we call as the wall mounted model, then we can have sting mounted model, and then strut mounted model. Let me just come to the individual model one by one so that you can get the idea about how we can do the aeroelastic testing in the wind tunnel, and then get some idea about the divergence or response of the system. Obviously, when I am talking of wind tunnel model, we will be not able to take the full scale model because the limitation in our test section of the wind tunnel, we have to take a scaled model of the full aircraft, either wing model, scaled wing model, or full aircraft scaled full aircraft model. Let me come to here now, wall mounted model. Whatever you are seeing, basically it is the planform view. This is one side of the wall, another side of the wall of the wind tunnel, and this is basically the aerofoil section, where this aerofoil section is the rigid. In this case, what we have usually we consider that the model which is made of means the material, model of this material will be such that it will be rigid. This model will be rigid. Whatever we are considering here, basically flexibility of this mounting system and the replication of the actual aircraft wing is considered through this supporting system, which will be given torsional stiffness. That's whatever we have considered here, aerofoil model, where one point we are considering the weight of the structure is acting downward, and the spring is mounted here. Basically, wherever we have connected the mounting rod, that is the stiffness of that rod is basically giving this torsional spring, and the aerodynamic load is coming due to the flow of the wind tunnel, that is U infinity, and we are taking certain parameter from here, from the tip of the aerofoil section XAC, the distance from the tip of the aircraft to the aerodynamic center XAC, the distance from tip of the aerofoil to the CG position, that is XCG, and then we are taking another distance, that is x naught, that is the distance of the elastic axis or the spring location, what we call as the elastic axis. Now let me come to the condition of equilibrium of this aerofoil, whatever we are going to test in the wind tunnel. There will be, obviously, when we are considering the equilibrium of the system, that is in terms of the moment equilibrium, requires that the sum of all moments about point O, that is the elastic axis. This is the point O, elastic axis. All the forces or the moments acting about this point O should be equal to 0. In anticipation of wing linear aerodynamics, we assume that the angle of attack alpha to be a small angle, such that sin alpha can be approximated as sin alpha and cos alpha can be approximated as 1. Now, if we consider the aerodynamic moment, that is MAC, aerodynamic moment, then we can take the this is aerodynamic moment about aerodynamic center. lift force multiplied by the distance between the aerodynamic center and the elastic axis, that is the distance between this x naught minus x AC. That's what I have considered here. Lift multiplied by x naught minus x AC. Then obviously the weight whatever is acting, that will be creating a moment, negative moment about the elastic axis. So W multiplied by x naught minus xg, the distance between the elastic axis and the CG location, that is the weight of the structure is acting through this point. So the distance is x naught minus xg, x naught minus xg, and the elastic restoring force k into theta. K is the torsional stiffness of the spring and theta is the torsional deformation. If the support were the rigid, the angle of attack would be alpha r, positive notch up, that is the elastic part of the pitch angle is denoted by theta, which is also positive when notch up. The wing angle of attack is then considered here alpha equal to alpha r plus theta. Means as we are considering here this mounting system is a elastic system. So due to air flow, whatever angle of attack initially we have set, it will not be continued to be same. It will be increasing. So we are considering here alpha is equal to alpha r plus theta. Alpha r is the rigid angle of attack, theta is the flexible angle of attack. For linear for linear aerodynamics, the lift force for a rigid support is simply can be calculated as Q dynamic pressure multiplied by the platform area multiplied by CL alpha into alpha R. That is the rigid lift, and the elastic lift will be QSCL multiplied by alpha R plus theta, whatever we have taken in the earlier case. And Q, the dynamic pressure, can be calculated as half rho infinity into infinity square. Rho infinity is the density of the air at the test condition, or means depending on what altitude we are doing the test, and U infinity is the forward velocity of the wind tunnel, the free stream dynamic pressure. And then MAC can be calculated QSC into Cmac. This is Q is the dynamic pressure, S is the cross sectional area, C is the chord length multiplied by Cmac, the moment coefficient at aerodynamic center at zero angle of attack, or with some angle of attack. We are combining together to take the total effect MAC. So now,
Sir,
yes.
sir, in the previous slide, uh, uh, you wrote that x naught minus xac. So what is x naught?
This x naught is the distance from the, if you come back here, x naught is this distance from tip of the aerofoil to the elastic axis. That distance is the x naught. This is x naught. Then distance between the tip of the aerofoil to aerodynamic center, that is xac, and xc is the distance.
Okay, got it.
So I have taken here L into x naught minus xac minus W, because this W is acting downward, so it will be creating anti-clockwise moment. So that we are taking here as negative. And obviously elastic restoring force, because when we are giving deformation in this direction, so elastic restoring force will be acting in this direction, that is k theta into theta. Okay, so that's why I have taken with the minus sign of this moment due to weight of the aerofoil section and the elastic restoring force. These two are negative. in the consideration that moment is means clock is positive, anti-clockwise moments are negative. In this case, MAC we have considered in the clockwise direction, lift also creating moment about the elastic axis as in the clockwise direction. So now I am coming to this for the simplification. What I take for a thin aerofoil theory, the that is the for the thin aerofoil section, and when we are considering subsonic aerodynamics, then CL alpha can be considered as 2 pi. So after getting all these values, I am just substituting in that earlier equation. So QSC into C max plus QSCL alpha r plus theta multiplied by x naught in minus XAC minus W into x naught minus XCG, that is equal to K theta. I am taking that right hand side and rearranging this equation and solving for theta, we will be getting theta equal to this. So the theta terms are here. If you look at here, we have one theta term here and theta term is here. So we have, if we take that QS into C into C max plus Q into S CL alpha multiplied by alpha r multiplied by x naught minus XAC. Then from here it is minus W multiplied by x naught minus XCG. Then whole thing divided by K minus this term, whatever we have taken it here. So K minus QSCL alpha x naught minus XAC. So this is the denominator term where alpha r and q are specified at the total lift can be when these two values are available, when alpha r and q, the dynamic pressure is available, specified, then we can calculate total lift of the lift and also the response of the system. The dynamic pressure at which divergence occurs, that is basically coming from our this consideration when the denominator becomes 0, that is the point of instability, and in this case QD can be calculated as just taking this denominator equal to 0. So simplifying QD can be calculated as K by S CL alpha multiplied by x minus XAC, x naught minus XAC. This is the dynamic pressure and then taking this relation half rho infinity square, substituting this, we can calculate infinity divergence, that is twice K divided by rho infinity S CL alpha x naught minus XAC. This is the theoretical value. Once I know the value of K, the stiffness of the rod, the density at that altitude, cross platform area of the aerofoil section, CL alpha, that is 2 pi in this case, and x naught minus XCC, then I can find out the theoretical value of divergence speed. Now let me come to the experimental procedure. Often, suppose we are taking this CMAC, that is coefficient of movement about elastic aerodynamic equal to 0, and we are taking x naught equal to x naught and CG are at the coincides, then these two will be equal to 0. When the moment due to weight will be cancelled, and it will become finally we can calculate from the this equation. So what we are taking, this is 0, this is also we are considering as 0, then whole thing divided by SCL alpha into alpha r. If we divide that, then we can get this equation. So alpha r divided by qd by q minus 1, and multiplying this, rearranging the expression, we are getting this relation, that is basically q by qd. We will be getting this relation, theta by q equal to theta by qd plus alpha r. Let me just show you the derivation once again. So it is theta multiplied by qd by q minus 1. This is equal to alpha and dividing whole equation by okay, let me just simplify first. Theta in qd by q minus 1. This is alpha r theta. So whole thing divided by qd. So it will be theta plus divided by q equal to theta by qd plus alpha r by qd. So suppose for a particular value of, experimentally what we can do, for set of value of q, let's say 0.1, okay, some means depending on the speed of the wind tunnel, let's say whatever wind tunnel we have in our aerodynamics lab, that is, it can go up to 28 meter per second. Suppose I am starting from, let's say, 5 meter per second. Then we can take under that, it will be half rho infinity square, whatever value I am getting. Let's say that is correspond to q1, then I can record the value of theta. Means we are giving a initial angle of attack. In addition to that, whatever additional deflection will be able to measure, means the aerofoil section will be experiencing, that we are considering as theta 1, let's say. Similarly, q2, I can get theta 2, and set of values of q, set of values of theta 2, I can measure experimentally. Then I can come to this plot where theta by q will be take the non-dimensional value, and this will be theta. In this case, I am just rearranging, means plotting this with respect to this. So let's say whatever we are getting here, theta by q by theta. So as per our final derivation, it is a straight line equation. We may get some scattered point and draw a mean straight line. And slope of this, inverse of the slope, that will be 1 by qd, is the information we will be getting from the slope of the curve. And from here, once I am able to measure the slope, I can take 1 by slope. This will give us the divergence speed experimentally. So this is the theoretical value of divergence speed, whatever we have calculated here, theoretical value of this, and experimentally whatever we have measured for different value of q, the values of theta we have measured, and then we can make a plot of this, and drawing a mean straight line, we will be able to get the slope, and from that slope we can calculate what will be the divergence dynamic pressure. Up to this, is it okay?
Yes, sir.
So this is the model what we call as the wall mounted model. Means in the wind tunnel wall will be setting a fixing mechanism, and the aerofoil section will be mounted in the test section. And once we will start the wind tunnel, depending on the velocity, we can calculate what will be the dynamic pressure, and from the dynamic pressure, obviously when initially we'll be giving some angle of attack, that is called rigid angle of attack, but just by rotating this one, rotating the position of this rod, we can change the rigid angle of attack, and then with the rigid angle of attack, after the flow has started, whatever additional angle, rotational angle, if we once we measure, then we can find out, subtracting that from the alpha r, we will be able to calculate theta. That is the way we do the experiment, and we need to take the values theta by q and theta, and we will be able to draw a mean straight line like this with respect to theta by q and theta. So this slope is basically 1 by qt, whatever we are getting here. Okay, so this is the way we do the experiment. Means theoretical value will be able to get from here once we are able to measure the torsional stiffness of the rod, and torsional stiffness of the rod, we are able to measure the platform area of the wind tunnel model, aerofoil section, CL alpha. In this case, we can take CL alpha as 2s pi for thin aerofoil under subsonic flow, and the distance between the elastic axis and the tip of the aerofoil we can get from here. Sorry, actually it is coming as x naught minus xsc. So the distance between the aerodynamic center and the elastic axis, obviously this part I have to take theoretically, and then substituting that I can get the theoretical value of qt. Wherever if you look at here experimental data only what we have to do, for several set of values of q, I'll be able to measure the theta. I don't need to measure any other information from the experimental data or experimental model. I need to measure the value of theta and value of q. Obviously, value of q I can get it once I know what is the forward speed in the wind tunnel. I can calculate the value of q, and theta I can measure from the measuring device. We have to put a sensor or through a laser measuring system, laser beam can be placed, and then we can measure the the rotational deflection of the that aerofoil, whatever we are mounting in the wind tunnel. So is it okay? Is there any doubt? Okay, whatever I am thinking, I will stop here. If you have any doubt related to nonlinear elasticity or this first model, whatever we have discussed, wind tunnel model with a the model what we are calling as the wall mounted model, that is wall mounted model, whatever I have described here. We will be discussing other two, that is sting mounted model and strut mounted model, that in the next day I will be discussing about that. If you have any doubt related to this wall mounted aerodynamic model, you can ask me. Whenever you are coming to the campus, then I can show you that model is there in our aerodynamics lab. I can show you that internal model, whatever we have there in the aerodynamics lab. It would be nice if you can do a experiment and get some idea about that experiment related to finding the divergence speed of the wind tunnel, which is mounted on a spring. Do you have any doubt here? You want to ask something, or I will close the session now because you are facing some network issues. I don't know, maybe whatever network I am using here, it is not proper. Sometimes it is giving disturbance.
So, sir, when you will be giving the assignment and by when will it be due?
Okay. Okay. Before closing it, let me just discuss about that, and then I'll be giving the group wise that information so that you can do the test. Perform the MATLAB coding and make the calculation. Let me come to that. This assignment, first assignment, I'll discuss with you now, and then I'll upload it in the next day so that you can do it. See, in this, what I have asked, derive the formulation to calculate response of nonlinear single degree of freedom aeroelastic with following combinations and generate plot with non-dimensional stick parameters. So what I have asked here, several combinations. First I have asked a linear aerodynamics model, an elastic model, quadratic nonlinear aerodynamic model, linear elastic model, where I will be asking group wise alpha r values. See, this I have given some data for considering that there will be 4 groups, but I think I have to divide into more number of groups because you are around I think 40 people are there, so probably 8 groups we can
30.
think of. No, today it may be 34, but as per the roll list, I get it is 40. Total 28 from BTech and 12 from MTech batch. Okay, total 40. So I'll give you the distribution of. You want to have 5 groups, 8 people in a group. It is okay.
Sir, but can we make the groups by ourselves? Because
that also you can do. You can then give me the information about that. 8 people in a group.
yes, sir.
Okay. You can decide and then give me the A, B, C, D, E up to E groups, and then I'll be giving you the data related to group means information means. Is it clear? Whatever you have to do in this assignment. See,
Sir, but
first you
8
have
people
to
will be too much.
too much. Then five will be okay. 5 per group.
Yes, sir.
5 is okay. Or
I
you
think
can
8
do.
is I think 8 is okay, sir, because it has 7 parts, so 8 is okay, sir.
Yeah, actually several models you have to make the derivation.
I
But
think 8 is
8
okay.
will be any. You just let me get the information to whatever groups you are thinking. Okay, then by next day I'll be giving you this information. What
Sir,
are
what you have
the
to do exactly? Can you explain once again?
you have to take a non-dimensional model of single degree of freedom system where I have given certain parameter. See, I have given certain parameter related to this. For linear model, you need to have values of alpha. I have given those values and then Q bar. So with this information, first you have to make the derivation to find out the response of the system. And see, whatever you will be able to calculate actually analytical solution for alpha r equal to 0. I'm saying for non-zero alpha r, you have to write a computer program in the MATLAB where you will be able to extract for different values of r. Considering the
So your voice is breaking too much, so we can't understand anything.
uh, I'll I'll explain this whenever we will meet, and
So your
by the
voice is
time
not
I'll
clear.
be not
Voice is
clear.
breaking, sir. So no, sir.
No, sir, your voice is not clear.
Network is there. Next day, on second assessment.
Okay, sir.
Okay. Okay. Okay, then I'll close the session to today's class. Next day, explain about this assignment, and then I'll ask you to do the program, a MATLAB program. Okay. Okay. You can now leave.